Hello everyone and welcome back. So now we're going to be talking about impact. So it's what happens when two things collide. There's going to be a lot of interesting physics we can do here and some pretty amazing equations. So first off, why do we care about impact? Well, think about a bouncing ball, like this tennis ball right here. The quality of a tennis ball is actually measured by the height of its bounce, like how much of the original height does it have each time. It's going to drop by actually a same fraction every single time. And this quality can be quantified by the coefficient of restitution. That's saying how much of the energy is left after the ball bounces. So the ball bounces once, how much of its kinetic energy does it actually have left? Now, if the coefficient of restitution is some fraction of the energy that was in the ball to begin with to the energy at some other point, do you think we can figure out what the coefficient of restitution for the ball is by comparing it after subsequent bounces? I think we can. Or with pool balls, you want to be able to predict the trajectory and speed of a ball after it's struck by another ball. But to do that, one thing you have to understand is, well, not all that energy is going to make it into kinetic energy. Someone's going to be lost as heat and as sound and as due to friction. So if we knew what that was, how much energy was going to be lost, do you think we can figure out what the velocity of ball B is going to be after it's hit by ball A? What do we need to know to understand that? Well, impact is going to help us figure that. Impact occurs when two bodies collide during a very short time. Like a hammer striking a nail, or a ball striking a bat, or two billiard balls colliding. The term we need to remember is there's something called the line of impact. It's a line through the mass centers of the colliding particles. Now there are two types of impact. Central impact, where they collide along the line of impact, and an oblique impact, where the line of impact is not along the line of impact. Their velocities are along the line of impact for central impact. And then for oblique impact, the velocities are not along the line of impact. There we go. Let me make sure I actually say it correctly. I think it's right there. There is an angle to the line of impact with their velocity. And this one, the angle is 0. Okay, for central impact, the velocity of the objects are along the line of impact. And the line of impact is simply a line through the particle's mass centers. Now, when they contact, they deform if they're not rigid. And energy is going to be transferred between the two particles. Okay? Energy is going to be transferred between the two particles. Part of this you could say is like this is kind of like spring energy. You know, the spring is going to deform here, and with that, it will cause them to contract, compress. So right here, we have kind of like a spring that's been compressed here as well. So they are storing energy, and they're going to release it and cause a transfer of energy and change their velocities. Now there are two primary equations when solving impact problems, and you can figure out their derivation from the book. The first one, which is simply conservation of momentum. Okay? Conservation of momentum. This can be applied along the line of impact. Now, the issue we run into is that there's usually two unknowns. We know what velocity A is after the impact, but not velocity B. But we don't know either of them. Then we're going to have to determine what that second unknown is using our coefficient of restitution, which is marked with E. And that's going to be that measure of how much energy actually makes it into the balls after the impact. You know, what fraction of the energy makes it there? Because not all of it's going to make it into it. So coefficient of restitution is simply a ratio of their velocities before impact to their velocities after impact. Velocities before impact to the velocities after impact. And notice this is relative velocities. Okay, relative velocities here. And these did switch on purpose, just so you know they were meant to switch. So if we know what E is, then this gives us a second equation necessary for us to solve for both of our final velocities. So conservation of momentum and our coefficient of restitution are going to be very, very helpful. Now, in general, it has a value between 0 and 1, and there are two limiting conditions that you need to think of. One is a completely elastic impact. In a perfectly elastic collision, no energy is lost, and therefore, the relative velocity equals relative approach velocity of particles. They bounce off each other. This is the thing you see with gases. All those little gas particles, they're colliding all the time, but it's completely perfectly elastic impacts. Thank goodness for that. Plastic impact is when E equals 0, which means that their separation velocity is 0. That can only happen in one case. They come in with some velocity, and then they are stuck together. They don't move. They have collided, and then now they are attached. So these are the two cases for us. Now, you might be very surprised to see that glass actually has a very high coefficient of restitution. Probably just never bounced glass off of glass before. It's very, very rigid, which means that a lot of the energy gets transferred. Very, very rigid, so a lot of the energy gets transferred. Okay, so yes, that's it for this time. We'll stop here. And next time we'll go into energy losses from impact and how we can calculate those. So thank you for listening. I hope this helps you, and I'll see you all next time. Bye-bye.